we are going to see the full wave AC voltage controller, which is also called as bidirectional AC voltage controller. Okay. So this is your circuit diagram, which is bidirectional AC voltage controller, and we are going to see this operation with the help of the RL load. Okay, and you have since you should have the current flow in both the directions. You should have two thyristors which are connected in anti-parallel. One thyristor will carry the positive current and the other thyristor will carry the negative current. Okay, and you have your AC voltage source, which is a fixed magnitude and fixed frequency. Okay, and you have two thyristors which are connected in anti-parallel, and you will be connecting your load. In this case, the load is your RL load. Okay, and the load is connected across this arrangement, and the output voltage is measured across your load. Okay, and the AC voltage controller, as we have already seen, it is going to convert the fixed AC voltage into variable AC voltage, but frequency is not varying. Okay, frequency is also fixed. Okay, so AC voltage controller is a converter which converts fixed AC voltage into variable AC voltage, and the variable AC voltage will be of variable magnitude only, not the variable frequency. Okay, now what you have to do is, during the positive half cycle, the thyristor T1 is turned on. Okay, and you have to choose a proper alpha firing angle value depending upon your requirement. Okay, so you have to first decide at which angle you have to turn on your thyristors. Okay, so at alpha you will be turning on your T1. So current that is going to flow from the source through your T1, through your load, and back to the source. Okay, so this is the case when during the positive half cycle. Okay, next, during the negative half cycle, this side will become positive and this side will become negative. So thyristor T1, it is automatically turned off by line commutation. Okay, now your thyristor T2 is forward biased, and if you release a gate pulse to thyristor T2, then it is ready to conduct. Okay, so at pi plus alpha, you will be giving a gate pulse to T2. So current, it will flow from this side, which is now positive, and through the load and through your thyristor T2 and back to the source. Okay, so this is now the current flow. Okay, so during the positive half cycle, T1 it is going to carry the load current, and during the negative half cycle, T2 it is going to carry the load current. Okay, and you can see the waveforms for this AC voltage regulator. This is nothing but your input voltage Vs. Okay, your input voltage Vs, which is your sine voltage, sinusoidal AC voltage. Okay, now at alpha you're triggering the device T1. Okay, so when you trigger your device T1, the output voltage, it is going to follow the input voltage. Okay, so from alpha, and the waveform which we are seeing here is the discontinuous conduction mode. Okay, so wherein your load current, this I0 is your load current. Since the load is RL load, the load current, it is going to have the two components. One is the steady state component, which is sinusoidal one, and the exponential component. So the resulting waveform will be this. Okay, from alpha to beta, the thyristor T1, it is going to carry the load current. So whenever your thyristor T1 is on, the output voltage, it is going to follow your input voltage, which is your Vs. Okay, so from alpha to beta, the output voltage is same as your input voltage Vs. Okay, and from beta to pi plus alpha, since no current is flowing because of the discontinuous conduction mode, no device is conducting, so output voltage is equal to 0. Okay, and when your thyristor T2 is turned on at pi plus alpha, the thyristor T2 it is going to carry the reverse load current. Okay, and from pi plus beta to pi plus, from pi plus alpha to pi plus beta, you will have your reverse current flowing in the load. Okay, and from pi plus alpha to pi plus beta, the output voltage, it is again, it is going to follow your input voltage. Your input voltage during that time from pi plus alpha to 2 pi, it is negative, and from 2 pi to pi plus beta, this point is pi plus beta, it is positive. Okay, again the load current, it reaches 0 at pi plus beta. Then from pi plus beta to this instant is 2 pi plus alpha. Okay, from pi plus beta to 2 pi plus alpha, you will have your load voltage which is equal to 0 because there is no any current flowing through your load. Okay, again you will be turning on your T1 and the process, it is going to continue. Okay, so you have converted your fixed AC voltage into variable AC voltage, and if you adjust the value of your alpha, your voltage magnitude, output voltage magnitude, it is going to change. Okay, so if you change your alpha value, you will be able to change your output voltage value. Okay, so this is the output voltage waveform and current waveform for your AC voltage, single phase AC voltage controller with RL load, and the condition which we have seen here is the discontinuous conduction mode. Okay, now that is what it is explained in this slide. Okay, so you have your current which is discontinuous conduction mode, the current which reaches 0 at beta, which is the angle which is called as extinction angle. Okay, so next is, now we have to derive the RMS value of the output voltage waveform. Okay, so for that you have to take your output voltage waveform, and from that waveform you have to derive the RMS value. Okay, now see, you need not derive the average value for AC voltage controller because the output is AC. Okay, for inverters also we did not derive the average value, we have derived only the RMS value. Okay, so your V naught RMS, it can be derived from your output voltage waveform, which is nothing but, as usual, we have to integrate your waveform over a full cycle, or you can integrate half the waveform over a half cycle. Okay, so 1 by pi, your output voltage is present from alpha to beta, and that is same as your input voltage. So input voltage square, you have to take Vm square sine square omega t d omega t to the power 1 by 2. Okay, so if you that is substitute for sine square omega t, you will get 1 minus cos 2 omega t by 2, and if you do the integration, you will get this value. Okay, so you have to integrate your d of omega t, and you have to integrate cos 2 omega t. Okay, if you do that, you will get d of omega t, the integration of d of omega t, it is omega t, and you have to substitute alpha to beta, and the integration of cos to omega t, it is sine to omega t by 2, and the limits, it is varying from alpha to beta. Okay, so after substituting the limits, and finally you will get your RMS value of the output voltage, which is Vm by root 2, 1 by pi, square root of 1 by pi beta minus alpha plus sine to alpha by 2 minus sine to beta by 2. Okay, so this is the RMS voltage waveform of single phase AC voltage controller with RL load, and the current is taken as discontinuous current.